Okay, cool. um, Hi, everyone. Welcome to our review session. So we prepared some material based off of your responses to the poll that we put up. And it seems like graph contraction was the most requested. So we're going to start with that, and then we'll go through the other topics. And yeah, feel free to ask questions, and hopefully this is helpful. I will start with the graph contraction. All right. Let me know if you guys can't see this, but hopefully you can. Okay, graph contraction. Yay. Fun stuff. So what exactly is graph contraction? So graph contraction is this idea of making a graph smaller in order to compute different properties of the graph in parallel. So if you remember back when we were studying algorithm design techniques, we talked about divide and conquer, we talked about brute force, and we talked about contraction. Contraction, this is like a similar thing to that contraction, except this is specifically for graphs. So when you do contraction for graph contraction, what you're going to first do is like partition the graph into different blocks. Then you're going to contract each block into a single vertex, drop any internal edges, usually, depending on your like application. For some reason, if you wanted to have internal edges or self edges, then you could keep those. And then finally, you would want to reroute the cut edges to their corresponding super vertices. And then you would recurse. So you would recurse on the quotient graph, which is the output of this contraction. This is a quotient graph. And then finally, you would expand. So you use the result from recursively solving to compute the result for the input graph. Fun stuff. So there's two types of contraction that we talk about in this class. We have edge contraction first. So what we do in edge contraction is we contract based or like defined based on the edges. So what you do is you flip a coin for each edge. So in this example, we flip heads for this edge, tails for this edge, so on and so forth. And then you're gonna create partitions based on the edges that flipped heads and all the, for the vertices that this edge is on, all the other edges coming out of this vertex also flipped tails. So then you're going to contract this into one single vertex, which is here, and then you keep repeating this until you have one final vertex at the end. So let's talk about like what this means. So what is the probability of selecting an edge on a cycle? Does anyone remember? No worries. That is totally fine. I get that. Okay, so if we want to consider the probability of contracting an edge on a cycle, what we want to consider is a cycle has, when you consider a vertex on a cycle, sorry, not a vertex, an edge on a cycle, we're going to flip or contract it if this flips heads and all other adjacent edges flip tails. So there's a 1/2 chance of this flipping heads. And then we want to consider all the other edges flipping tails. And there are at least 2 other adjacent edges. So we want the probability that those also flip tails, so which is 1/2 times 1/2, which equals 1/8. So the probability of selecting an edge on a cycle ends up being greater than or equal to 1/8.
Yeah, I have a question. So I remember like in lecture, when we talked about the edge contraction, like there was this like probability of 1/3. Is that like when we, instead of like flipping the coins, we use like random priority for each edge? Is that where we got the 1/3?
I would imagine. So I imagine what you would do is something like, instead of heads and tails, it's like, what is the probability that the
center is
the highest, exactly, and that would be 1/3. So that's where that analysis would come from. Is it less than? I might have flipped it. Yeah, it might be less than. You're right. My bad. Thank you for catching that. So does that make sense so far? Okay, awesome. So now we want to, the thing about edge contraction is that it doesn't really perform well on other types of graphs. Like it performs well on graphs that are cycles, but if I give it a graph that looks like a star, what's going to happen is that you can really only contract one edge at a time, right? So it's not super efficient. You end up doing a lot of unnecessary work. So that's why we then talk about star contraction. So star contraction, instead of flipping a coin for a vertex, we're going to flip, instead of flipping a coin for an edge, we're going to flip a coin for a vertex. So a vertex becomes a center if it flipped heads, like A, and it becomes a satellite if it flipped tails. And if it's a satellite, it's going to pick one of its neighbors that did flip heads to contract into. So in this example, C picks B as its center, and E also picks B. So our partitions look like this, with the different colors. So now our question is, what is the expected number of satellites for a graph with n prime non-isolated vertices? N prime over 2 is close. It's going to end up being n prime over 4. And we're going to go talk about it why. So we want to consider, like, for each vertex, what is the probability that V is a satellite? And that probability is going to be equal to the probability that V flipped tails and the probability that some neighbor of V, let's call it U, flipped heads. So this is equal to 1/2 times 1/2, which is 1/4. And we have to consider this for all the vertices, which is why this ends up being n prime over 4. If we're going to be more precise, it actually ends up being greater than or equal to n prime over 4, because it's not just the probability that a neighbor U flips heads, it's a probability that any of its neighbors flip, at least one of its neighbors flips heads, which is greater than 1/2. Greater than or equal to 1/2. So that's why we end up expecting n prime over 4 satellites to be in a graph. Let me do star contraction. Any questions about star contraction in general? Okay, I'm gonna keep going. So some just really quick facts. Edge contraction, if you do like a greedy vertex matching, I think this is covered a little bit in the textbook, but it'll select a lot of edges within 2 factors of the optimal solution for vertex matching. And edge contraction does O of n work and log squared span on cycle graphs, but doesn't perform super well on general graphs, which is why we have star contraction, which uses star partition. Star partition takes O of n plus m work and log n span. And then the entire like contraction will take O of n plus m log n work and log squared n span. So when we give you, or like not when we give you, but when you're thinking about using contraction to solve a problem, there's like some general approaches that you can think about. So if you're trying to solve a problem with contraction, you can first think about doing some sort of pre-processing, then contracting the graph into some smaller graph, then recursing, and then doing some post-processing. And if you want to like try to come up with some sort of parallel contraction technique, you want to make sure you're using some sort of randomized thing, like coin flipping, random permutation, et cetera, et cetera. And ideally, your contraction technique should allow for good performance in expectation for any graph. Unless you're trying to do it for a specific type of graph, then I guess you would want it to like be good for that specific type of graph. And in some cases, you might want to maintain certain invariants depending on like what you want your contraction to do. So we're going to talk about invariance in a second, but I see that there's a question. What is a cycle graph? A cycle graph is a graph that where like every vertex, I guess, is involved in a cycle. So something like this. I think that's like a informal definition, but yeah. So let's talk about some of those invariants that I had just mentioned. So here's a question. Does edge contraction preserve the following properties? So if a graph is acyclic, does edge contraction preserve that? You guys can put like a yes or no in the chat. Okay, I see 2 yeses. Yeah, okay, so let's talk about the first one. So the first one is yes, because I guess the way I think of it is like you're not adding edges when you do edge contraction. The third one is also a yes. If you want to, I think this is actually a problem from a midterm, one of the practice midterm. So there's a more thorough explanation in there, but you can kind of think of it as like when you do edge contraction, for every edge that you contract, you're also like taking away one vertex. So you're always going to maintain the whole like m is equal to n minus 1 thing. For cyclic, it's actually no. And here is like a little counter example for why. If we had a graph that was like a cycle and we contracted 2 of these or one of the edges, then you're just going to end up with like a graph that's just one edge. It's kind of sad, a lonely graph, but yeah. So what if we asked, I mentioned this is one of the midterm questions. I believe it's practice exam 2, question 6, if you do want to take a look. There's some other questions in there that are not like these questions. And what if we ask like similar questions about star contraction? Does anyone have any ideas for any of these? Or I guess for now, let's just go through the first 3 and like for the sake of time, and we can talk about the rest later. Oh, yes, someone has their hand raised.
For the first one, I would think no, because we could think of a star and a lot more of just dotted vertices with no edges. Like say a 10 star and then like 1 and then 3 non-vertex, and then we could contract the entire star into 1 vertex, so there's no more edges left, but there are still vertices left.
Yeah, that is very true. That's a good example. So this would be a no. And these two the next two would be a yes and a no. So for the yes, you can kind of think about like, if every node has degree less than or equal to 2, it's kind of like almost like a path, I guess. Like you can't have any more edges coming out of this. So if you do star contraction on this, you're only going to contract in like a couple vertices like this. So you're not adding, you're contracting like parts of the path together. I actually have another example here for the first one. But if you consider like some graph with a lot of edges, and then you just contract 2, I guess, of these partitions, you're going to end up with a graph with just 1 edge. And now this has less edges than vertices. And for the graph with degree less than or equal to 3, you can kind of think of almost like a binary tree. And if you contracted just like one part of this tree, you would end up with a graph where the center vertex has degree 4, which is not what you wanted. Cool. Questions? Why is 2 true again? So 2, a graph with every node having degree less than or equal to 2 is kind of just like a path. So if you contracted something on this like path like graph, whatever you contract is not going to, when you convert into like one giant vertex, there's only one edge coming out this way and one edge coming out this way at most. So there is no, like there, you maintain this like maximum of 2 out degrees or edges coming out. Yeah, I guess it is just a tree. Wait, I'm a little confused about the chat. Okay, so the definition of a tree is, I believe it's no cycles and the number of edges is equal to n minus 1. I can tell if there are any other questions. If there are any other questions, feel free to interrupt me. And I'll also be posting these slides with the annotations, so yeah. Okay, let's go through one more problem if you guys are ready. So this is a question, again, from a practice midterm. It's exam 1, question 6, but we're only going to look at a specific part of it. So we give you this code that it creates this set F, which is a set of edges where you pick the minimum weight edge incident on some vertex V. So if this was our like input graph, we're picking from A, we're picking the minimum weight edge incident on it, which is this highlighted one. Same thing for D, the minimum weight edge is this highlighted one. And you kind of repeat the same thing with B, C, and E. So you end up picking these edges, and your next, I guess, graph kind of looks like this, where you have V and F looking like this. And then what we're going to do is take this and contract each tree in F into a single vertex. So what contraction technique do you guys think would be useful to use on this case or in this problem? I see one person saying edge. Okay, lots of different answers. So I think the most efficient thing to do in this, or in general, when you're doing graph contraction, it's typically more efficient to use star contraction over edge contraction, because edge contraction doesn't necessarily perform well on a bunch of different types of graphs. I think in this specific case, it might seem like it performs well, but if I had a graph that looked like had more edges and didn't really have a cycle because everything in here is a tree, then it wouldn't perform as well as star contraction. So what we can do in this case is perform star contraction as we've like described in class. So we're going to contract, I guess, all of these trees using star contraction until there's one remaining. And the cool thing about star contraction is that it preserves the tree invariant. So if I could do star contraction on a tree, the like quotient graph from star contraction will still be a tree. So why do we care about this? The reason we care about this is because that means the number of edges will decrease with the vertices. So we can stop when there's no more edges. And we have a bound on how the vertices will decrease. We have that like n prime over 4. So we can kind of also put a bound on how long it'll take. So if we use star contraction as described, we would expect this to take O of n work and O of log squared n span in expectation. There's a hand raised, yes.
Why is it log squared n and not log n, since we're used to doing it log n times?
Right. I think the reason is because if we go back to like our quick facts slide, so, oops, it's the one before this. So when we do star partition, we use log n for the partitioning, yes. And because we do it log times, it ends up being log squared n span once you contract the entire graph. So this question is asking us to contract the entire graph. So we would do log squared in one round, but in order to make it all into a single vertex for each tree, that would be log squared times log squared, which is why, sorry, log times log, which is why it's log squared.
Can I ask one more question of why then is it O n work, not O n log n work?
That is a good question. I think if you assume that the vertices are enumerated, you can then do star partition in O of n plus m work, which would then make, like if you then solve this as a recurrence, you have like the work of n is going to be equal to like the work of 3n over 4, because you expect about 1/4 of the vertices to go away, plus O of n. And if you solve this recurrence, it ends up being root dominated, which is why you can have O of n work. It's kind of similar to the recitation analysis that we did this week. But yeah, and the reason you can drop the plus m is because we are in a forest. So m is going to be less than or equal to n minus 1. Okay, no problem. There's a couple more questions. So in this example, yeah, I guess I didn't define which vertices could be the centers, but we could pick any of these vertices to be the centers. So like A and B could be the centers here, and E and C could contract into them. And with n and n decreasing by a constant factor, we have that the work is, oh, so you were answering the previous question. Okay, yes, awesome. So I think, yeah, in general, it's better to use star contraction if it's acyclic, like unless we're like explicitly asking you to use edge contraction. Star contraction just performs better on general graphs. Yeah. Okay. Let's talk about one more part of this. Sorry, someone is saying something. Go ahead. Oh, no, never mind. I thought someone was asking a question. Okay, let's go through one more question related to the same code. So same problem, but so we want to argue about how many vertices are in V prime relative to V. Specifically, we want to say that doing this like star contraction on this forest will remove at least half of the vertices. Does anyone have any ideas why? I kind of repeated the graph here, and it contracts to like just A and B. It's a bit strange of a question, but you can kind of notice that like each tree in F is going to have at least 2 vertices, because the trees are like defined by the edges, because we picked like we picked edges to put into F based on the minimum weight edge incident on some vertex, and each edge is going to be associated with 2 vertices. So therefore each tree is going to have at least 2 vertices. And then each tree then becomes one vertex, right? Because we're going to contract until there is a single vertex for each tree. Therefore, you remove at least half the vertices. Or is that at least? No, it is at least. Yeah. Any questions about that? Okay. Any questions about contraction in general? It's kind of a tricky topic. Less than or equal to V over 2. This part? Yeah, so we kind of want to argue that we're removing at least half the vertices. So whatever V prime we get, there's going to be less than or equal to v over 2 of these vertices. And the reason we can say that is because like if each tree has at least 2 vertices, and each of these trees then becomes a single vertex, then we kind of will be dividing, how do I say this? Each tree becomes a single vertex, and there are at least 2 in each tree. Therefore, like we are dividing the number of vertices by at least 2, because in like the worst case we have like A, B, C, D, dot, 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 and then each of these becomes a single vertex. So then there are now half the vertices in our contracted version. Does that make more sense?
Wait, why is it a forest like this? And how? I guess I'm generally confused. Why can we remove at least half of the vertices?
Yeah, so it's a forest just based on the way that F was defined, because we're just picking the minimum edge incident on V. We're not going to have any cycles because that would mean that there are 2 minimum weight edges, which isn't possible. And then some of these are disconnected, which is why it ends up being a forest. That's kind of just like based on how F is defined. And then the reason it kind of like divides in half, I guess another way of saying this is saying that like you're gonna have n over 2 edges, sorry, no, n minus 1 edges. You're gonna have at least n over 2 edges in your frontier. So it's gonna be like at least n over 2 edges in F, and then we're going to contract each edge. So we're going to reduce the number of vertices by n over 2, because we are contracting all of the n over 2 edges. Is that more confusing or less confusing?
Wait, so why do we know there are n over 2 edges, and how would that guarantee the recursive call why would the contraction step remove half of the vertices? Like, how do we know half of the vertices will disappear because of the contraction?
Okay, so the reason there's n over 2 edges, at least n over 2 edges, is because when we define F, we, how do I say this? So like each vertex will pick one edge, right? To be its like minimum edge incident on it. And then like a vertex, this vertex has a minimum edge that's different from this one. But in the best case scenario, each vertex that's incident on an edge will pick it. So we're gonna pick one for each vertex. But in the best case, 2 vertices will pick the same edge because an edge is incident on 2 vertices. So we're going to have at least n over 2 edges. Does that part make sense?
Yes.
Okay, awesome. So then when we contract these n over 2 edges, we're going to end up, we're going to contract each of these trees into a single vertex. And because each of those edges will be contracted, and if we have n over 2 edges, like let's say we have n over 2 edges here, this is n over 2 for whatever reason, and we have like vertices here. Each of these are going to be contracted into a single vertex. So we had n over 2 edges, and now we have n over 2 vertices. So that's like why it's like at least.
So a recursive call is actually a completion of the contraction. I thought the recursive call was like meaning one contraction call.
No. So like, this part is like completely contracting the forest.
Okay, cool. That makes sense. Thank you.
Okay, awesome. Okay, there's a lot of questions. Let me catch up. What would be tested for star contraction? I thought it was a topic on Monday's lecture. I believe you're being tested up until Friday's lecture. So I guess if they didn't cover star contraction on Friday, we can't test you on that. But I think it might be good just to like understand how it works in general, because it's very similar to edge contraction, just like on a different part of the graph. But yeah. Are we guaranteed it'll contract into one vertex though? I think like we're just continuing this contraction step until it does eventually become one vertex. If it didn't become one vertex, then I guess you'd be stuck in some sort of infinite loop. So in a sense, yes, if that makes sense. Like after you do all of the contractions, not just like one contraction. What if the coin flip resulted in A and B having the same heads and tails value? Then you wouldn't contract that, yeah. Okay, what if a tree is multiple layers? I think it is full completion. Okay. Did I miss any questions? Are there any other questions about anything contraction related? Okay, awesome. Okay, in that case, I'm gonna post these like annotated slides to Didero, and there is one more question, but I will post like the solution also to Didero if you do want to take a look at that. I think it's a cool question if you do want to take a look at it. And I will pass it off to the next TA, which is Vanshika, I think.
Yeah. Okay, cool. Let's see if this works. Is it showing up? It's not showing up yet. Let's fix it. Let me try this again. Sorry, my iPad's being kind of buggy today. So let's see. Okay, can you guys see this? Shortest pad slides. Great. Okay, cool. Yeah, so we're gonna do a quick overview of shortest pads and then do a couple problems. I apologize in advance. People were asking about people were asking about Johnson's problems on Diderot, but I couldn't find any good problems. So I'll try to find some before Friday. But if I don't, I think if you understand the stuff from the textbook, then it shouldn't be too bad. Okay. Cool. So before I talk about the algorithms, I think it's important to do a quick refresher of why the shortest paths algorithms that we talked about actually work. So like it basically comes down to two main lemmas, I guess, like statements that we use in these algorithms. The first one is the subpaths property, and this I think is used in basically every single shortest paths algorithm. And all it's saying is that any path which is a shortest path can only contain other shortest paths. So like if you had a path from, so yes, if you had a path from like from S to T, and then you considered a subpath from U to V, this path P prime also has to be a shortest path, because if it wasn't a shortest path, then you get a shorter path from S to T. So that's like the gist of what the subpath property is. And what this implies is that the shortest distance from S to V is less than or equal to the shortest distance from S to U plus the weight from U to V. And this is basically what's used whenever you expand your frontier. So you're building up shortest paths by taking a shortest path that already exists and adding on one more edge. Cool. So then the other property that we use often, or not often I guess, but it's like the main reason why Bellman-Ford works, and that's K-hop recursion. So this is also basically building off of this statement, but it's saying that the shortest path from S to V that uses at most K+1 edges, it has to be the minimum of the shortest path from S to V that uses at most k edges, or a path that uses at most k edges plus one more edge. So like this is basically extending on the subpath property, but like adding on a relationship between the shortest path and number of edges used. Okay, cool. Yeah. So then quick recap of what is used in which algorithm. So Dijkstra's basically only uses subpath property and it uses the fact that edge weights are positive. Bellman-Ford uses the subpath property and this k-hop recursion. And then Johnson's, I feel like Johnson's is like using the subpath property when it comes up with the potential function, but the rest is just Bellman-Ford's and Dijkstra's. Yeah. Does everyone recall the potential function for Johnson's and why that works? Yeah. Okay, if you are not sure, hit no or raise your hand and I can really quickly, it's like a 2-sentence explanation, I think.
Can you just go over it?
Yeah, sure. Okay, so we know that the distance from S to V is, so from this equation, right, we know that the distance from S to V is less than or equal to the distance from S to U plus the weight from U to V, right? So in Johnson's, we use Bellman-Ford to figure out all of these distances. Okay, but the problem is that these edges could be, some of them could be negative, right? So we want to remap our edges to have positive weights instead. So the way you can do that is just like rearrange this equation. So you know that the distance from S to U plus the weight from U to V minus the distance from S to V is greater than or equal to 0. And this is exactly what the new weight would be. So like the weight prime from U to V is the difference in the distances plus the original weight. So like I would say like you can put this on your cheat sheet, but if you like remember this equation and then you can rearrange it so that you get something that's greater than or equal to 0, you don't even have to memorize what the potential function is. Is that okay? Okay, cool. So this is just a quick recap table of all the algorithms. So Dijkstra's is the first one. This is the greedy priority queue based search algorithm. So it's completely sequential, has work O of m log n and span O of m log n. And my little memory cue for remembering why it works is that it basically relies on the assumption that your paths can only get longer as you add edges. So like basically the first time you see a vertex, that has to be the shortest path. The first time you pop a path to the vertex off the priority queue, that is the shortest path. Because adding more edges isn't going to make your path less costly. And this is why negative edge weights doesn't work. Cool. And then Bellman-Ford has O of mn log n work and O of n log n span. And it builds shortest paths with more edges from shortest paths with fewer edges. It's using that k-hop recursion that we talked about. And then an important thing about Bellman-Ford is that it can detect negative weight cycles, and does this by detecting if you get to considering paths of length n, and if your shortest distances haven't converged yet, that means that you have to have a negative weight cycle. We'll talk about that in the next bit too. Cool. And then Johnson's is solving the all pairs shortest paths problem. So like Dijkstra's and Bellman-Ford's are both solving the single source shortest pairs problem, but Johnson's is finding the shortest path between any pair of vertices. So this has O of mn log n work and O of m log n span. And it's my memory cue for this isn't really a memory cue. I mean, I guess it is, but it's just like, what is it? And it's just Bellman-Ford. And then you use your potential function to make the edges positive, and then you do a bunch of Dijkstra's. Yeah, so all of these works and spans are assuming an adjacency table representation. I think it's a really good exercise to figure out the work and span with other graph representations. And then something that could be really useful for your cheat sheet is to like make a template or a table of like how you do the work and span analysis for each of these algorithms. And then depending on like whatever changes you throw out, you like, oh, like let's say that your comparison function is no longer constant. or let's say that this is a true set.
To put on cheat sheet. Why did she not just make the fucking cheat sheet for everybody?
Okay. Yeah, I think you should make it yourself. That's my response to that. Cool. Yeah, so yeah, so if you do that, then you can kind of plug and play whatever tools we give you, and it should be pretty easy. Okay, moving on. All right, so we're gonna do a few true and false questions. So let's, oh wait, there's messages. Yeah, same. Okay. All right, so the first question is, does Dijkstra's algorithm always terminate? What do y'all think? Yes, it is true. Yes. Cool. Does anyone want to explain why? Is anyone not sure why? Okay. Yeah, so like quickly, it's just because you're always going to add every edge to the priority queue and you always remove every edge. So you can't do, yeah, it never revisits its vertices. It'll check every edge exactly once. Cool. So Dijkstra's algorithm always terminates. All right, next question. Does Dijkstra's algorithm always fail on graphs with negative edge weights? Yeah, it doesn't always fail. Yep, it depends on the order you visit in. Yeah, a one-edge graph is a very simple counterexample. You can also think of counterexamples which have multiple paths between vertices, because it also depends on what the source you pick is. So I think a general, like a rule of thumb is that like if the first time you see the vertex is using a negative edge weight, then that negative edge weight isn't going to be a problem. But like the problem happens when you see a negative edge weight later in the path, and it's not the first edge in the path. Because Dijkstra is assuming that when you add more paths, when you add more edges, your path isn't going to get shorter. Okay. Cool. So next question is, if a graph has a negative weight cycle, then Bellman-Ford will not converge after n iterations. Is that true or false? True. Yeah. Wow, you guys are killing me. Yep, this is also true. This is just like after n iterations, it's still going to be decreasing because of that negative weight cycle. Okay, so now what about the converse? If Bellman-Ford does not converge after n iterations, then the graph must have a negative weight cycle. Yeah, also true. Yep. I think the easiest way to see this is just look at the contrapositive. Oh, converge. I mean, so like in Bellman-Ford, right? You're gonna you have the original distances you found so far, and then in the next round, when you add on, when you consider paths of length at most k plus 1, you consider the new set of distances d prime, and if all of the distances are the same, then you say that d is equal to d prime, and that means that Bellman-Ford is converged to the true shortest distances, right? Because like if none of the distances changed by adding another edge, then you've necessarily found the shortest paths possible. Yeah, that's a good question. Yeah, so back to point 4, if the graph does not have a negative weight cycle, then you can say that any shortest path has to be simple, meaning that it doesn't need to use a cycle. And then that means that every shortest path would then have at most n-1 edges. So then it's guaranteed to converge before n iterations. Cool. So the last one is, Johnson's algorithm does not work if all of the edge weights from the dummy vertex are not 0. False by textbook. Yes, it is false. Does anyone want to explain why?
Is it because like of a non-zero additional edge added? It's kind of like when we say like, oh, we just add like a constant weight to like each edge.
So not quite. Like adding a constant weight to each edge doesn't work, right? Because because that'll mean that edges which have more paths which have more edges will be overly weighted. So like you could end up getting like making a path that was the shortest before no longer the shortest because you added too much of the constant to it. But I think the idea is like, as it doesn't matter if all of the edge weights are not 0 because like you're gonna subtract it in the end anyways when you do your potential with after you do Bellman-Ford, you'll end up subtracting that the edge weight you added on, so it's not actually going to affect the shortest path that you get.
Oh, yeah. So the extra weight is like included in the potential anyway. So when we add it to that potential, yeah,
exactly. Yeah, and then and then Marco and Eric's comment that like you don't even necessarily have to add the dummy vertex. If you already have a vertex which is connected, or a vertex which can reach all the other vertices, then you can just use that and add stuff in. Yeah, the next slide has the summary. So yeah, so it's true, false, true, true, false. Cool. Are there any questions about these? So what are you referring to Johnson's or adding the dummy vertex? Wait, I'm confused which one. Oh, adding the dummy vertex. You don't need it to be a strongly connected component, right? Because strongly connected component is saying that any vertex is reachable from any other vertex. All you need is that there is at least one vertex which is connected to another. Yeah, you know, it can be negative. I think Tamyar posted a really good comment explaining like exactly why the edge weights assignments for Johnson's don't matter. I recommend checking that out. But it basically boils down to like you'll add it, but you'll end up subtracting it again anyways. So it doesn't matter. Okay. Actually, I think it can't be negative. Yeah, I think if it's negative, you could end up making a path that isn't the shortest path shorter. I'll double check that. Anyway, Steven says it can. Yeah. Okay, I'll come back to Fiona's question. Yeah, I can explain the convergence idea again. So basically the idea is that, so in Bellman-Ford, right, on a certain run, if you're considering paths of at most k edges, you have some set of distances that you've already found for all the vertices, right? And then in the next round, you're going to find the paths with lengths at most k+1 edges. And so you have another set of distances d prime, right? So the claim is that if d is equal to d prime, which means that all of the distances for all the vertices are the same, so like dv is equal to d prime v for all v, then that means that adding on this new edge or increasing the length of the path did not end up making the path shorter, right? So then you can say that this means that that no matter how many more edges you add on, it's not going to end up making the path shorter. So like we can talk about it more explicitly. So like, you know that at k you have distances d, and at k+1 you have d prime, and this is the same as d, right? So when you add on another edge, like say when you go to k+2, that's not going to make your path shorter.
So if it's not shorter, is it already converged then?
Yeah. If none of the distances change, you've already found the shortest possible paths. Because your distances can only decrease, right? Because you're always taking them in.
Okay, thanks.
Mm-hmm. Is that okay? All right. I'm going to move on. I'll come back to the negative weight question. Okay. So let's do, I have like 3 problems to do. So let's start with this one, should be not too bad. So we want to design an algorithm to solve the longest paths problem for a weighted graph, and the edges could have negative or positive weights. The longest path problem is like the opposite of the shortest path. You want to find the longest path from, let's say this is a single source. You want to find the longest path from a single source S to all other vertices. So you're using to use Dijkstra's and flip the comparison function. So that doesn't quite work, right? So like the reasoning is like, okay, so remember again that Dijkstra's always assumes that when you add more edges, you can't do better, right? And like, so yeah, you guys are saying the same idea of like using a, like making it a max priority queue instead. It doesn't work, right? Because like, Dijkstra says that when you add more edges on, you're not going to do better. But like, the point is that when you add more edges on, you can do better, right? If you're trying to get a longer path. So like, just making it a max priority queue doesn't work. Yeah, so a couple of good ideas. So Michael said Bellman Ford take the max instead of the min. Yeah, so you can change Bellman Ford to keep the max instances instead, and then you'll be detecting positive length cycles. And then Elizabeth and Joanna both said you can negate all of the weights and use Bellman Ford. That also works. So the reason behind that is like if you want to maximize the sum of all the edge weights, that's the same as minimizing the negative sum of the edge weights, right? So if you flip all the edge weights, then that'll then you can just use standard Bellman Ford. Is this okay? I think Kuhn had a question. Yeah. Is it okay now? Okay. Cool. So if there are no questions, this slide just has the explanation. And then we'll advance to the next question. Okay, so this is the second choice path problem. So you're given a weighted directed graph G, and you want to find the second shortest distance from S to T in both M log n work and span. And you can assume that the edge weights are all positive. So if you have multiple shortest paths, like if you have ties for a shortest path, you still want to return the second shortest distance. Okay, so this problem is pretty tricky, so I have a couple questions for you guys to consider. So first is like, how does the second shortest path differ from the shortest path? And then what if you need the distance from, okay, so yeah. Use Bellman Ford to store a tuple. Can you explain what you mean? Do you mean like keep track of the, okay, yeah, so you guys are saying the first idea that I had when I was thinking of this. Okay, so I think, I'm not sure about using Bellman Ford and storing a tuple, but using Dijkstra's and storing a tuple doesn't quite work. And so like the reasoning is like, this tuple is what you're going to use in your comparison function, right? So then that means that like, how do you compare two pairs of like a shortest and second shortest, and like how do you compare two of those, right? Okay, you want to explain your idea a bit more? Yeah, so you could do that. I would say like don't put it in the yeah, don't put it in the priority queue, but you could, yeah, you could put it in a table. But let's say that you wanted to do this without using that extra space, like because like you're already keeping extra space, you're already keeping space for the distances, right? So like I don't want to store multiple things. Yeah, and then Rohan's comment for Christine's idea, that's correct. Yeah, you could have you could have the second shortest and shortest path overlap at some point. So if you remove the shortest path, you can end up finding the incorrect answer. Okay, so let's talk about these questions, right? So like the second shortest path has to use an edge that the shortest path doesn't use, right? So then how would you figure out? Yeah, do you want to expand on your idea? Yes, exactly. That's exactly right. So let me talk about that a little bit. So like the idea is, right, that like if you're looking at the shortest path from S to T, right, the second shortest path has to diverge in some case. Like let's say that this is an edge U to V, which the second shortest path uses, but the shortest path doesn't, right? So you know that the distance from S to U plus the weight of U to V plus the distance from V to T is less than the distance from S to T, right? Yeah, so then if you want to find the, you know that any second shortest path has to look at least like this, right? Like your second shortest path is this or worse, right? And so what you can do is basically loop through all of the edges and compute this value, right? And the second shortest path, sorry, this should be a greater then. And the second shortest path, yeah, that the second shortest path will be the path which minimizes this value while still keeping it greater than the distance from S to T. So you don't even have to like do any explicit checking of whether the edge you're considering is in the shortest path or not, because checking that the distance you get is greater than the distance from S to T will kind of cover that. Yeah, and then like Lindsay said, the complexity is just it's a single source shortest path plus O of M. So the O of M again. For what it's worth, the table solutions do work. I think it's fine, but I think this is a neat solution, which kind of like also it's a neat little application of the like the inequality I talked about earlier, right? The table generalizes the third best. Yeah, that's true. That's true. Although I think that there's probably smarter ways to do the best. I haven't thought about that. Yeah. Are you talking about the table solution? Yeah, so basically the idea is that, you know how like in Dijkstra's, in all these shortest path problems, you're finding a mapping from each vertex to the distance from S to V. All you'll do is also store, you can store the second distance from S to V. This is point notation. I'm saying delta 2 is second shortest. And so then every time you find a path and you try to update, you would check if it's smaller than the current minimum distance. If it is, then you move the minimum distance to the second minimum and update this. You check if it's smaller than the current second minimum and then update second minimum instead. So like updating the min2 that you found so far. And then you can generalize that to third, fourth, etc. I think at that point you probably want to keep like a heap or something instead of like keeping the sorted list.
I'm still a little confused about just the standard approach we talk about by checking like M edges. So how do we get the shortest distance from V to T? Do we also get that from the single source shortest path?
No, so for that you have to, what you could do is you can run Dijkstra's on the reverse graph instead, so that, and then run it from T. So that'll give you the distance from T to V on the reverse graph, which is the distance from V to T on the original graph.
Oh, okay. And
Yeah,
then
sorry,
like basically we can assume, can we assume that basically like how when we flip the edges, the shortest path from one vertex to another basically doesn't change. Is that what we are?
So yeah, as long as you like flip the order of the vertices as well. So like if you find the shortest path from V to U in the reverse graph, that corresponds to the shortest path from U to V in the original graph.
Yeah. Okay.
Yeah.
Okay. I see. So then, like, essentially, we are running like two diatrace sequentially, which makes the asymptotics.
You can run them in parallel. You can run the two diatraces in
yeah.
parallel.
Right. Okay.
Yeah.
And then, like, we just try like every edge possible
Yeah.
to okay. Thanks.
Yeah. So Owen, I think I didn't explain that really well, but like the point is that the second shortest path has to differ in at least one edge. So it could differ in more than one, and you can see that by like saying that. Okay, so let's say that this is the edge UV that it differs in. It could be true that like you also have divergence here, right? Like there's multiple places where it diverges from the second shortest path, from the shortest path, but like your distances will find the it'll find like that divergence basically, right? Like you still want this to be the shortest path from S to U, and you still want this to be the shortest path from D to T, right? Because like again with the subpath property, right? Like if this wasn't the shortest path from S to U, you could change it to be the shortest path from S to U, and you would get a smaller second shortest path. Yeah.
Is it possible that the U and B, like here, we basically just assume like between U and B, there's like one edge. Is it possible to have like multiple edges that still form like the second shortest distance?
Yeah. So like your second shortest path could diverge in multiple places, but we only need to care about like one of those edges.
Oh.
Yeah, we're just considering one edge at a time. Sorry.
We are only considering. Yeah, because I was thinking like the reason why we can get like we only have like this one extra O of M is that we just need to check like this we just need to go through like every edge and see like by adding one edge like if it's possible to form like the second shortest distance. But then like I realized we can add multiple edges maybe and form the second. So I'm not sure like how we can just try by trying like M.
Yeah. So I think your question is basically similar to Owen's, because it's like saying that like, okay, how do you know that like it's only one edge that differs? That's not what I'm saying, right? I'm saying that it differs in at least one place. But like if you consider a path which diverges in more than one place, right? Like this path that I drew here, there is some edge on here, which when you consider this distance will be like the minimum possible. So like, okay, so let me actually make this out better. So like, let's say that let's say that your shortest path from S to 2 looks like this, and then you have three edges where it diverges. Right. So let's say like A, B, C, and D, right? So you're gonna check the edge A, B, B, C, and C, D, right? So when you check the edge, A, B, right, you're guaranteed that this is the path that you find for the distance from S to A, right? Because you know that this is the shortest distance from S to A.
Yeah.
Okay, but then it's not necessarily true that this is the shortest distance from T to, like, you don't really know what the shortest distance from T to B looks like, right?
Yeah.
Actually, wait. I think it does have to go through here. Yeah, if you assume there's no other edges here, I think it does have to go through there. Because let me make this for a sec. Yeah, so let's say that there's no way to get to B from anywhere in here, right? that means that you can go from T to D, and then you have no choice but to go to C and then go to D.
Yeah, and then
yeah.
I mean,
Yeah,
I can ask after this session. It's fine. It's fine. I don't want to take too much time. Yeah.
I think your question is good. It's tricky. Are there other questions about this problem?
Would this algorithm work if you check every vertex not in the shortest path instead of checking every path?
I'm not sure what condition you're checking for every vertex.
As in the shortest path to a vertex, and then from S to that vertex, and then from that vertex to T. But then assuming that that vertex is not part of the shortest path.
I think it doesn't work if the shortest path from S to T contains all the vertices. Like that's definitely possible, right?
Okay, yeah, I see how that. Okay.
Yeah. That's a good point. Okay, I'm gonna move on to the next problem in the interest of time. Okay, so this is the solution. Okay, so last problem is one negative edge. So yeah, okay, so you're given a. Wait, should I stop here or should we move on?
I don't know. What do you guys want to do? Like, do you guys want to do more of this, or do we want to do a different topic? Say yes if you want more shortest paths, and no if you want. I think the next topic is treats and tables and stuff.
Oh.
Right?
Yeah, I think it's treats and BSTs.
Ah, okay.
Yeah, sure. Actually, wait, the solutions are all on the slides. So I'll post these, and then if you have questions about that, you can ask on Twitter. I would say think about this question on your own first, and there's a couple hints here which could help. Is that okay?
I think I thought I saw like quite a few yeses for like staying on this, so we can like go through this problem and move on.
It shouldn't be too bad. Okay, cool.
Okay.
Yeah, so in this problem you have a weighted directed graph, and there's exactly one edge with a negative edge weight. And so this edge is E. And you want to design an algorithm with m log n working span, which determines whether the graph contains a negative cycle. And if it doesn't have a negative cycle, you want to return the shortest distance between S and T in the graph. So something to think about, right? If there is a negative cycle, is it possible for E to not be in the cycle? And then what can you say about the weight of E if there is a negative weight cycle? So I guess for the first point, right, like if there is a negative weight cycle, then E has to be in it because it's the only possible negative edge weight, right? So now, given that, let's say that this is what this is like the picture you're looking at. So you have the edge UV, and then you have a cycle, and then it keeps going, right? So if we say that, so if we say that this is the path P, which makes it the rest of the cycle, given that you know that it's negative, right, you can say that this means that P plus the weight from U to V is less than or equal to 0. It's less than 0, right? Yeah, exactly. Yeah, so you know that the weight from U to V is less than U to V, or that like P is less than negative the weight from U to V. Cool. Okay, so then what could you do? So I guess like figure out if this is true. Remember that like this bound is O of m log n, right? And there's only one negative edge. I think you'd want to run Dijkstra's from V, but yeah, you can remove the edge U to V, and then when you run Dijkstra's from V, right, you'll get the shortest path from V to everything else. So then you'll know what this distance is, and if this inequality is satisfied, then you have a negative. Then you have a negative cycle. Okay, cool. So now like the second part, right, is you want to find the shortest distance between S and T in the graph. We should have the label S and T. This is S and this is T. So let's say that you found that UV is not on a negative weight cycle. Then what can you do? Actually, this is kind of a misleading picture. So there's two cases to consider, right? Either the edge is on the shortest path or it isn't, right? Why can't you use Bellman? That'll break the work and span bound. Yeah. Okay, so let's say that we ran Dijkstra's from S, right? Then we have the distance from S to everything else, right? And then what must be true if the shortest path decreases when you add in this edge U to V?
Could we use a flag to see if we hit U twice? Like since we know it's exactly U, couldn't we just put a flag like we have hit U once, we have hit U twice, and we have hit U 0 times?
Sorry, I don't follow what you mean. Like, do you mean like hitting this, like using this edge or not?
Like just keep inside the comparison function how many times we hit U.
Yeah, but like the thing is, Dijkstra's won't work with it won't work with the negative edge weight still there, right? It's not guaranteed to work. So you can't run Dijkstra's if the edge is there or not is there. So let's say that you remove this edge. Yeah, Elizabeth, do you want to share that to everyone?
Okay, so my idea was we first remove UV and then we run Dijkstra's to find the shortest path without UV. And then after that, you would use Dijkstra's to find the shortest path from S to U and then from V to T, and then add the weight of U to V. So then you like bridge the gap. And if that's shorter than our previous path, then that is the shortest path. Otherwise, it's not.
Yeah, that's exactly right. Yeah, and so I think what Callan said is also right. You want to find the shortest path from V to T, but the idea is correct.
How do we detect the cycle then? Don't we still need to detect the cycle from there?
Yeah, so you detect the cycle before you do this. So like you detect the cycle by finding the shortest path from V to U in the graph with the edge UV removed. And if this shortest path is less than negative times the weight of UV, then you know that you have a negative weight cycle. And so then shortest paths aren't defined. So you would just return there's negative weight cycle. And if there isn't a negative weight cycle, then you do what we just said. Yeah, it's with the UV edge removed. What do you mean? How we find the UV? Yeah, you're given the weight of UV.
Wait, I guess I'm just wondering, like, how do we find a cycle? Like, why do we know this edge the UV edge? Like, is it we need to find a negative edge first?
So you're given that this edge UV has a weight UV which is less than 0, right? And you want to determine whether it's on a cycle or not. So the way that we said you can do that is you find the shortest path from B to U on the graph without this edge, right? And you get some distance P, right? And you know that you can do this because there's no other negative edges. So like Dijkstra's will work perfectly fine. And then if there's a negative weight, if this is part of a negative weight cycle, you know that this must be true, right? P plus the weight from U to V is less than 0. So a way to check whether this forms a negative cycle when you after you find P is to check whether P is less than negative times the weight from U to V. Is that okay?
So if it's not in a cycle, then there would just be no path beside UV that connect these two vertices, right?
That's not necessarily true. You could still have a path from V to U that connects V to U, which doesn't use the edge UV. But the point is that it's only going to be a negative weight cycle if this inequality is true. So
like,
it's okay
I
to
can
have
also
cycles.
have another edge from U to V and say the negative edge weight is like -2, and then another edge is like weight of 1. The sum is also negative, right? But it's not necessarily a cycle.
Yeah. Was that your question, Nathaniel? Elaborating on whether cycles are still allowed?
Oh no, I was just asking with like what Stephen said.
Oh, okay.
Wait, but if
Yes.
that's the case, it not necessarily hold, right?
Wait, can you recap the algorithm one more time, please?
Yeah, sure. So the first thing you're going to do is remove the edge UV, right? And then you run Dijkstra's from V, and you only care about the distance from V to U, right? So this gives you this value P, right? Space. Then you check if P is less than negative of the weight from U to V. If it is, then you have a negative weight cycle. Right, otherwise, you do the following. So you run Dijkstra from S, and then you also run from V or run from T on the reverse graph. I think it doesn't matter either way. And then you check if the distance from S to U plus the weight from U to V plus the distance from V to T is less than the distance from S to T that you got from this run. And if this is true, then you return this distance. Otherwise, you return the distance from S to T.
Is this a directed edge from UV? If so, like, why do we need to remove it to run the Dijkstra's from V? Because like, won't the Dijkstra's from V not even use the edge UV?
Yeah, you're right. I guess you don't need to remove it. Yeah, because it could still use a cycle, but it's a positive cycle, so it wouldn't help. Yeah. I think it's okay if you don't remove it, but you have to remove it when you run Dijkstra from S anyways. So they do. Yeah, steps 1 to 3 are sufficient to detect a negative weight cycle. Steps 4 and 5 are to find the shortest distance.
So are we not allowing multi-edge?
No. No, I think, no, you are. You can still have multi-edges. I think we should probably move on to the next topic. We can talk about this at the end, or you can message me privately. We can talk about it too. Is that okay?
Sure.
Cool. Yeah. So that's all I have. This slide deck has additional problems, and I'll post down to Arrow. So yeah.
Are we?
Are you? Yeah. Do you want to go ahead?
Oh yeah, sure. Just making sure it's actually my turn.
Yeah.
Okay. Let me share my screen. But by the way, everyone can hear me, okay?
Yeah.
Okay, so let's go over some concepts and some problems in TREEPs and BSTs. So first of all, just some important definitions. All right, so first of all, let's first define what is a full binary tree. This is one term that everyone often, a lot of people often forgot. The definition of a full binary tree is basically a rooted tree where each node is either a leaf, basically has no children, or it's like an internal node which has 2 children. Right? So basically a full binary tree is like a tree that either have, that's basically like there's no node with only 1 children. Right? It's always like either 1 children or 2. I mean either 0 children or 2 children. So yeah. So the other important concept is that basically the definition of TREEP. A TREEP is basically a BST with a priority function P, right? Where basically each node not only has a key and a value, but it also has like a priority. And basically 2 invariants have to be satisfied at the same time. The first one is called BST invariant, where basically the tree has to be a binary search tree, right? So basically like everything in the left subtree of a node has smaller key and everything in the right subtree has to have a larger key. And then there's one additional invariant, which is the heap invariant, where basically the priority of the parent is always larger than the priority of the children. So when constructing trees and manipulating trees, one important technique we use is called rotation. So here's an example of a rotation, right? Suppose like we want to suppose like somehow like right now 2 is the parent of 1, right? Suppose we don't like that, we want 1 to be the parent of 2 instead, right? So we can perform a rotation over these 2 nodes. So right now, note that like we have subtrees A, B, and C, right? Note that in this case, everything in A will have key less than 1, everything in B will have key between 1 and 2, and everything in C will have key between 2 and 3, right? So suppose somehow we want 1 to be the parent of 2, then we just rotate it like this. Now 1 is on the top and 2 is its children. And how do we want to fill in the 3 subtrees? Well, first of all, since A is less than 1, A has to go here, right? So, and then B, since B is between 1 and 2, B needs to go here. And then we have C that goes here. Right? So this is called rotations. So basically, like when we call it like going from the left to the right, we call it rotating to the right, right? Because it's like we turn this bar like to the right, kind of, and then the backward transformation is called the rotation to the left. Basically, this is the concept of rotation, tree rotations, and this is important because we can use rotation to rebalance a regular BST into a TREEP. Let's say like this over here, we have a totally valid BST, right? Where like 1, 2, 3 are the keys here. Right? Suppose like we want to transform this into a TREEP instead by randomly assigning priorities. And now we have priorities like this. Right? So the first number is the key and the second number is the priorities. Note that like this is a valid BST, but it's not a valid TREEP, right? Because like the priority up here is like smaller than the priority of its children. That's not good. So to turn this into a valid TREEP, what we want to do is, well, first of all, we got to make sure that 3 is on the top because 3 has the largest priority, right? So we do a rotation like this, and it ends up like that. And then it's still not complete. It's still not a completely valid tree because around like this node still have a lower priority than this node. Right? So we just need another location at the rotation at the lower level, and then it gets us here. Okay. So basically, in more complex VSTs, we just do this at all levels until like the heap invariant is fully satisfied. And this technique is used in join mid, the join mid function in Sheep, right? And in textbook chapter 43, we actually talk about like how to derive most other functions from join mid. So like it's basically like split and basically everything. So basically like pretty much all the functions we've been using from Sheeps can be derived with just split and join mid. So that's why rotations is like super important. So now we've talked about like the basic concepts of creeps and BSTs. Let's try to go over some practice problems. Before we start, is there any questions on anything before? Okay. In that case, can move on. So the first problem is this, right? So basically, you're given a BST, right? This is not a creep. This is just a regular BST. You're given some range xy, and you're supposed to count how many subtrees of BST falls completely within this interval. So a subtree falls in an interval if every single node in that subtree has a key within this interval. Right? So for example, in this case, if we want to count the number of, oh sorry, I missed the bottom part. So basically, our goal is to count how many subtrees of the BST falls completely within this interval, and a leaf counts as like the smallest subtree possible, right? And in this case, note that like we're not using like empty leaves. The leaves actually has a K and a V, and like over here, sorry, I missed the V here. There should be a V, and we need to write a function BST count, which takes in the BST and a range, and basically needs to return the number of subtrees in T that completely falls within the range XY. So just as an example, suppose we have a BST like this, and our range is 5 and from 5 to 20, right? Then how many subtrees are there that's in this range? Well, there should be 6, right? Because the subtrees rooted at these numbers are completely within the range. So 6, the subtree is just itself. Since 6 is within the range, it's a valid subtree. Right? 8, the entire subtree here is within this range. Right? And then 9 is in the range. We also have 10, right? This entire subtree, all 5 of these nodes are within this range. And then we also have 12 is in the range, and also 18. Right. So note that like the range is like inclusive on the left and exclusive on the right. So 20 is actually not in range. I mean, even if 20 is in range, like this, the subtree rooted at 20 would still not be a subtree within this range because 22 is not in the range. Right. So one challenge of this is that like the root does not have to be in the, like for a particular subtree, the root does not have to be in the bounds, but like it could still contain subtrees that are in the bound, right? So for example, like in this subtree here rooted at 20, 20 is not in the bound 5 to 20, but it has it contains like a Trojan 18, and the subtree rooted at 18 is actually in the bound, right? So this is like particularly challenging part. Into minimum maximum reduced value of keys. So actually so basically, first of all, this in this problem right now we just have a BST. So yeah. So actually the okay. So actually, since like there's not enough votes for tables and augmented tables in the topics, this this slide is supposed to focus on just the troops and BSTs. So yeah, so all of these problems are supposed to be solved with just recursive BST techniques. So yeah, so one way to do this is to first implement a function that basically like just checks whether a subtree T is okay, right? By okay, I mean like it's within range, completely within range XY. So how do we do this?
We check if it's the leaf, we check the leaf in the bound. If it's node, then we check that the left and the right is in the bound. So we recursively call it twice for the node, and then we just check if the leaf is in the bound.
Yes, exactly. Right. So this is what we do. Right? We just simply so basically if it's a leaf, then we just check the key itself. If it's in the bound, we return true, otherwise we return false. If it's a node, then we basically first have to check whether the node itself is in the bound. And then we need to check if the left subtree is completely in and the right subtree is completely in. Right. So here's a question. Do we actually need this part? Can we if both left subtree and right subtree are inbound, do we still need to check if the key is inbound?
No, because of the BST property.
Yeah, exactly. Right. Like if both left subtree and right subtree are inbound, then the k is definitely inbound. So technically we don't need this part. Yeah, but the older slides included them in. So now we've implemented the helper function of is subtree okay, which basically takes in the subtree and the range and returns whether it's completely inbound or not. Now let's implement the actual BST count. So it should have a similar structure like this. So anyone has any idea on how we can do this?
For the leaf, you would just say like if subtree is okay, add like the leaf or like your total, you add 1. But for node, you would do is subtree okay, is 1 plus, and then like is the subtree okay for the left and the right?
Yes. Yeah, I think that's how you do it. Except like when you're doing left and right, you do recursive calls on BST count to get the numbers.
All right, sorry, that's what I meant.
Yeah, I think I understood what you meant. Yes, that's exactly how you do it. Right. So first of all, you would for the base case, you just check if the key is in range. If it is, then it's 1. Otherwise, it's 0. Right. And then if is subtree okay, and then like if it's the node case, then you first check if the whole tree is okay. If it is, then you would just return BST count. You just recursively count everything on the left subtree, everything on the right subtree, and then plus 1. Right. If it's not okay, then you basically plus 0 instead, right? Which we can omit. So you just count the recursively count the subtrees. So let's quickly talk about the cost bound of this approach. So so we know that like is subtree okay? What is the cost of is subtree okay? Let's go back to is subtree okay. What is the cost of this function is subtree okay? Can someone tell me work and span? You can assume that these two parts are ran in parallel. Okay,
Can we assume memorization of some sort, or do we need to recursively repeat every time?
I'm sorry, can you repeat the question? I didn't hear it.
Can we assume memorization for left and right subtree because we recalculated that, or we not calculate? Are we assuming no memorization?
There's no memorization. That's a topic way later in this course. So yes, the cost would be O of n work and O of log n span, right? Because basically like it's basically the recursion is like work of n equals 2 times work of n over 2 plus O of 1, right? And then it's leaf dominated, so we end up with linear work and log span. So given that, what would be the cost of BST count? Well, since we're already running a bit late in time, I guess I should go a bit faster. So basically the cost is, so since like is sub tree OK costs O of n work and O of log n span, right? Then the work of BST count here, just it's the recurrence is basically like 2 times work of n over 2 plus O of n, where the O of n comes from calling this is sub tree OK here, right? So the total work would be O of n log n here. And then span similarly here, assuming we compute BST count of L and R in parallel, then we should have O of log squared n span. Is there any question on this simple approach to this problem? Okay, if not, we can move on. So the question is, can we do better? Right now, like this algorithm is like not very efficient because when we're doing is sub tree OK here, technically is sub tree OK recursively computed is sub tree OK for like L and R internally, right? And then we're calling is sub tree OK again when we're recursing on BST count in the next round. So there's a lot of wasted work in this algorithm. So can we divide a new algorithm such that we have better work and span bound for this problem? So can we do better? Well, the answer is yes. And the intuition of the better algorithm is that in order to avoid like repetitively computing is sub tree OK for the same nodes over and over, we can try to compute is sub tree OK and BST count at the same time. Right? And we can use this technique called strengthening, like remember that from like way earlier in this course. So basically, instead of having BST count to just compute the number of available subtrees, the number of subtrees within this range, we strengthen the problem by writing this helper function that not only returns the count, but also return whether the subtree rooted with basically like the entire tree is within the range or not, right? So for example, in the leaf case, we would just see whether the key k is within range or not, right? And it is. We return 1, and also a true, indicating that the entire subtree rooted at this node is within range. Otherwise, we return 0 false, right? So how do we complete the node case?
We combine the numbers, and if it's true and true, then return true.
Yes, exactly. Right. So basically like the entire node is only within range. The entire subtree rooted at this node is in range if and only if both L and R are completely in range. So what we should do is we compute we recursively call the helper function on L and R, and then we get the counts A1 and A2 and the Boolean values B1 and B2. Right? Basically, we say if B1 and B2 are both true, then we should return A1 plus A2 plus 1 and true, meaning the whole tree is also the whole tree is also in range, right? Otherwise, we just return A1 plus A2 and a false, indicating the whole tree is not in range. It is not entirely in range, right? And then when we return for the elder function, we just we just call on the inner function, inner helper function, and just discard the final Boolean value and just return the count. So what is the cost of this implementation? Is it better? Well, the work here, since right now, like each round, like the extra work at each round is only constant time, right? Because, well, basically everything here other than the recursive calls have constant work. So the total work would just be O of n, because this recursion is leaf dominated. And the span here again is just O of log n, because there's constant span other than the recursive part, right? Assuming we do these two parts, assuming we do these two recursive calls in parallel. So yeah, this is the better solution. Is there any questions on like this problem? Like any questions so far? Wait, like for some reason I cannot see the chat. Okay. Oh, sorry. And then we'll bring cultural DCNS. Okay, this is pseudocode. So don't worry about that and too much. Yeah, this basically, I mean, this approach does not really have similar idea with DP. Another approach would have similar idea with DP if like we first pre-compute, if like we still use the old is subtree approach, but instead of like changing it to this, we just memorize it. Yeah, DP is a topic we'll talk about later in this course, so don't worry about it for now. It is not going to be on the exam. You should not use any kind of memorization technique in this exam. It definitely will not be required. Don't worry. If you don't know what DP is, it's fine. It's not a part of this exam. Okay. Well, in that case, let's go over a second exercise really quickly. So this part is basically, I think it's an additional exercise in one of the recitations. So show that given a set of nodes x1 all the way to xn with associated keys and priorities, all distinct, we basically need to prove that the tree associated with these nodes is unique. So how do we do this? Well, usually since we're dealing with a structure, since we're dealing with like a tree structure, right? The general approach to deal with this kind of problem is usually just like induction. Right? So basically, when we're given a set of n nodes with distinct key and priorities, what is definitely going to be the root of the tree? Yeah, right, exactly. The one with the highest priority, right? Because in order to satisfy the heap invariant, we have to have the node with the highest priority as the root. Yeah, therefore, based on this heap invariant, the root has to be a node with the highest priority. Right? So basically, we can formulate a proof like this. So the base case is like if it's an empty tree, by default, it's unique because it's empty. And then like the base case should also include the one node case. I'll add that into the slides. Where if it's only one node, then there's only one possible tree, right? Because it's just this one node. So the induction hypothesis here we're going to do is for any set of D nodes with distinct key and priorities, right, where D is between 1 and n-1, it results in a unique tree. So then in order to prove that, and then it's like the proof would be for a set of n nodes, right? We have a fixed root, right? We know R has there has to be some node has to be the root, right? And this root is unique. And then the two subtrees will also be like the set of nodes in each subtree will also be unique because of the BST invariant. Everything smaller than R will go to the left, and everything larger than R will go to the right. I mean, in terms of keys. And then since the root is gone, the size of L and R is n minus 1 at most. Right? So each is a unique tree based on our induction hypothesis. And for the n node tree, the root is uniquely determined, and its subtrees are also uniquely determined by the BST invariant. Right? So the tree exists and definitely is unique. So this is a pretty straightforward proof. So if you ever have to prove some kind of stuff for trees or structures like that, like this would be like a way to do it. Okay. Yeah, I think that's all I have for this topic. Is there any questions on any of the trees or BST parts? Okay, I assume we're good then.
Yeah, we can go on to the last part that we had prepared, which is like BFS and DFS.
Sweet. Can you guys see the screen?
That's good.
Cool. Okay, yeah, so a little bit over time, but luckily DFS and BFS are pretty easy, so we can just blast right through these. Sweet. So this is the basic kind of DFS algorithm. Just a quick review. My pseudocode maybe looks a little different than the other ones, but yeah, this is just kind of what I wrote up. So remember, we have the graph, the set of nodes that we've seen, a current node. If the node is in the set of nodes that we've seen, we return some value depending on what we want to use DFS for. We add it to the nodes that we've seen, and then we continue DFS iterating over all the neighbors of V with the new set and the new nodes. Cool. And just quickly to go over the DFS runtime, it's E plus V for array implementations. So this is good if you have nodes that are numerable, and then it's E plus V times log V for table implementations. So this is when you are not able to enumerate the nodes. Okay, yeah, and this kind of depends on, this runtime depends on these two being, well, at least for the array implementation, this E plus V depends on these being constant time. Cool. Yeah, when I was coming up with problems, I didn't really know what to come up with, so I just stole from LeetCode. So you might have seen this problem before, but we can go over it with our DFS algorithm. So for this problem, we're given a 2D sequence of ones and zeros. The ones represent islands. So this is, for example, one island. There's some more islands somewhere in this 2D sequence. And the islands are connected by adjacent ones. So these two are connected, these two are connected, and so on. But the ones are not connected diagonally. So for example, these two ones do not form part of the same island. And we want to find the area of the largest island of ones. So in this case, it's this island here, right? 1, 2, 3, 4, 5, 6 ones. All of the other islands are smaller. So given this problem, how can we solve for the solution? Anybody want to take a crack at it? How can we solve this? Hopefully using DFS.
Make every one a node, and any connected up, down, left, right ones have an edge between them.
Yeah, so that's actually a really good way to think about it. So if we think of these ones as nodes, and then each of these nodes have an edge next to them, then we can think of this entire 2D sequence as kind of a not connected set of nodes, and then we just have to find kind of the biggest set of nodes that are connected, right? So great intuition, and we can take a look at how we can use that graph representation, and we can solve it using DFS. Cool. So, right. So this is kind of based on what your colleague suggested. Assume that we're at a vertex GV in the graph, where V is an ij coordinate. So that's how we're going to represent these nodes with ij coordinates. We can use DFS to find the area of the island that stems from that location. So for example, if we have, I is this row, j is this column, then this would be our current node. And we can use DFS to find all of the nodes that are connected, right? Okay, so then the second step is we want to actually run DFS all. If you remember this algorithm, it basically just runs DFS for every single node. Then we can keep track of the largest area island that we've seen while running this DFS all algorithm. Cool. And I think, yeah, one of your colleagues mentioned this in the chat as well, this run from each vertex idea. Sweet. So we have kind of two steps. And let's take a look at this first step first. Running DFS to find the size of an island given a starting coordinate. So that kind of sounds kind of like just like a generic DFS algorithm. So we have, this is basically the same algorithm from earlier, just with some additional things. So same thing, right? The graph, the set of nodes that we've seen already, and the current node. So V here is representing an ij index here. So if V is in X or V is out of bounds, we obviously want to return 0. And because that's not an island and can't be an island. But like one of your colleagues said earlier, if it's not a 1, right? If this location in the graph is not a 1, we also don't really want to count that as a node. We just want to find the ones. So if it's a 0, we can also just return 0. So this is exactly the same. We add it to the set of nodes that we've seen. And so we have a few modifications here, right? Earlier we saw that we just run DFS. Now we want to keep track of the total area that we've seen. So actually, I think that might be a typo in here. Whoops. Let me fix that real quick. I think we actually want 1 plus this DFS. Not for every node. We just want 1 plus the other ones. Cool. Oops. Okay. So why do we start out with this area 1? Because we want to count the current node as an area, right? So the current node that we're at is going to be this area 1. And then we just run DFS through all of the neighbors. In this case, we know that there are actually exactly 4 neighbors per node, right? We have I minus 1, I plus 1, j minus 1, and j plus 1. Some of these are going to be out of bounds or they're going to be zeros, but our base case takes care of that, right? So we run DFS through all of these neighbors, adding their respective areas, and finally we just return the total area. Any questions on this algorithm here to find the area of an island?
Say like in exam, when we are asked to describe like this sort of algorithm, do we need to also stress that, describe like how we are to represent like the neighbors of each vertex? Because here it's kind of like we cannot use adjacency matrix, adjacency sequence, right? Because it's not enumerated. I guess we can make it enumerated if we do, yeah.
Yeah, so I think either the test will tell you if it's enumerated or not, or if it doesn't tell you, you can state your assumptions, and then we'll probably just grade based on those assumptions. So yeah, you're right. If it's not enumerated, you can actually just label all the vertices in the beginning to make it enumerated. But otherwise, you can use a table representation, and that'll just be a little bit more costly.
Yeah, and we do need to say like what structure are we using, right?
In terms of like adjacency table, adjacency sequence.
Yeah, when we are describing our algorithm.
Yeah, I think if it's not given to you in the problem, it's nice to just say that's the one you're using, so that when we're grading, we don't make any assumptions ourselves and grade it incorrectly.
Okay.
Question in the chat, is it enumerated by index in matrix? Yeah, you can enumerate it that way. You can enumerate it as a 2D sequence. You can enumerate it as just a 1D sequence of, you know, n squared or sorry, but row times column indices. Yeah, so I don't really, I probably should give that assumption, but I don't really talk about. So you can represent this however you want. How do we create the graph given the 2D matrix? Right. So in this case, you can actually do it a variety of ways. You can, so like we talked about, we can make an adjacency sequence. We can make an adjacency table. And then depending on your runtime bounds, you can choose either way. In this case, I think I just kept it as a 2D adjacency sequence where the neighbors are just the 4 directions from each index. So for example, we can run like seek.nth to go into the rows and then seek.nth to go into the columns. And then to find the neighbors, we can just call seek.nth on like row -1, the same column, and kind of similar idea for all 4 of these neighbors. Yeah, so that's kind of an abstraction, right? So the one, we can say only the ones are the vertices. And in that case, we skip the zeros because they're not vertices. Or we can say the zeros are also vertices, but we just skip them because they don't matter to us anyways. Does that make sense? Okay, cool. Any other questions before we move on? Sweet. Okay. So we just finished that first step, right? Where given a starting vertex, we can find the area of the island that is connected to that vertex. And we notice that even though we branch out in 4 directions each time, we have this set of seed nodes. So if we see a 1 again, we won't you know, accidentally add another area to it. Okay, so now for step 2, which is we want to run DFS all over everything so we can find the largest one, right? So here's our DFS all algorithm. Graph, set of seed nodes. So this time we keep track of like a maximum area, and we go through for every vertex in this graph. We can say we can run DFS on starting with that vertex, and we can say the area returned from that DFS call. We can compare it to the maximum area so far, take the max between those two, and that way, once we see in all of the islands, then we can return this max area. And we make sure that we don't kind of run DFS through multiple islands multiple times. So for example, if we start running DFS here and we see this node and all of these nodes, by the time we get to here in the DFS all algorithm, we don't run it again because this will already be in our set of nodes that we've seen, right? And it'll directly jump to the base case and not add additional area. Cool. So that was basically the first problem with DFS. Does that make sense to everyone? Any questions? Okay, sweet. Yeah, so DFS, super easy to use. Cost analysis. So we use standard DFS, and we actually, if we take a look at the algorithm, none of the functions we use are actually non-constant. So we have some additions, and we just turn constant time values for everything. So yeah, standard DFS runtime O of E plus V. And we can actually condense that for this problem to just O of V, since we only have 4 edges, at most 4 edges per node coming out of each node. So it's just constant number times V. Sweet. BFS. Quick algorithm review. So for BFS, a little bit different. We only care about a current frontier that we have and a set of nodes that we see. Remember, if the frontier is empty, we can return something depending on what we want for the algorithm. If it's not empty, then we add the current frontier to the set of nodes we've seen, and then we build a new frontier based on the neighbors of all the nodes in the current frontier that we haven't seen before, right? And then we call BFS on this. So super quick, easy review. Runtime. So there's two different runtimes again. So one for array implementation, one for table. Linear work and d log v span for array implementation. D is the what's it called? The diameter of the graph. Yeah, so that's the longest, shortest path of the graph. So the longest possible, like shortest path between two nodes you can take. If that doesn't make sense, feel free to ask. And then for the table implementation, a little bit longer. So e log v work and d log squared v span. Cool. Good stuff to have on a cheat sheet, by the way, in case you need a quick reference on the test. Okay, so this is our problem, also taken from LeetCode. This one's pretty easy, pretty simple. It would go by pretty fast. So given a binary tree, so a special type of graph, I guess, return a list of the average values at each depth. So at depth, so starting from the root, this is depth 0, right? The average value is 1. At depth 1, the average value is 2 plus 3 divided by 2, so 2.5. And then the average value here is 5.5. And finally, the average value here would be 8.5. So this is the algorithm, or this is the problem. And let's think of a way to solve it. Does anybody want to volunteer to come up with a way to solve this, perhaps using BFS? Yep. Good answer in the chat. So at each round of the BFS, we can calculate the average of the frontier values. Cool. So yeah, super easy algorithm. So here's how we can modify the generic kind of BFS algorithm to do this, right? So we have, similarly as before, the frontier set of nodes we've seen. This time we're going to keep track of a list. This is just going to be our output once we're done. So yeah, if the frontier is empty, then we just return the list that we've computed. Otherwise, the rest of this stuff down here is basically the same as what we've seen before from BFS. The only thing that's different is we want to run this averaging function over the current frontier, right? So we can probably reduce over the current frontier, adding everything, and actually want to divide by the frontier size. So quick typo here. We might want to divide by the size of the frontier. Sweet. Okay, and then we just take this average and constant onto our list, and we'll keep going. Yeah, so hopefully you guys can see how that might work for this problem. Quick cost analysis. Yeah, if you look at the textbook for the BFS, all we need is each round to be linear in terms of the frontier and logarithmic in terms of the, or logarithmic span in terms of the number of nodes. Sorry, a lot of typos here, my bad. Span. And this will guarantee that our total algorithm runs in the expected runtime for BFS. And this is actually something that might be helpful on the exam if you're asked to write a algorithm for solving something using BFS or DFS in some expected work and span. You can just make sure that each round fits within the expected work and span for standard BFS or DFS, and that'll make sure that the overall algorithm is what you expect as well. Cool. Any questions on, isn't parallel BFS mlog and work? Right, so in this case, I also assumed we're using a sequence or an array implementation. So E plus V work. But yeah, if you're using a set or table implementation, then parallel BFS would be M log N would, E log V would, I guess. Good question. Any other questions? Sweet. If that's it, then I think we're done.
If you have any other questions about, I guess, anything we talked a bit about today, feel free to ask. And good luck on the exam.
I have like a question regarding like one of the practice exam, but I already posted it on Diderot. I don't know, like I guess I should just be waiting for the response from TA later.
Which question was it? We can just talk about it now.
It's the practice 2 7B. I think.
Let me pull it up.
Yeah.
7B.
Yeah, I think I might have some misunderstanding about the definition of like max sub neighbor, because like just in this case, like I'm a little confused about like for 7B, like the second inequality in the end statement. Say like if we look at just like the edge like from 1 to 5, in which case the V is 5. The max sub neighbor in this case is like 9, right? And then like the max prenom will be 6. So I'm not sure, like yeah, in this case, like, oh wait.
I think the max prenom is 9 for vertex 5, right?
Oh, it's 5. I thought like the max prenom is like just looking at like a V's neighbor. It cannot be like in the subtree. I could totally be wrong though. As I said, like I might be misunderstanding the definitions here.
So, no. I was just saying that the maximum prenom is 9 because that's what it says in the example under part 5.
Oh, okay. Oh, the max prenom is 5. Okay. Or 5 is 9. Okay. So yeah, I guess I'll just read over that.
It said max prenom is the maximum preorder number of its subtree. So like the subtree of 5 would be 6, 7, 8, and 9, and the maximum number there would be 9.
Oh, okay. Yeah, somehow like I was like looking at the 0.4. Like the 0.4 says like it's the prenom number. Oh, okay, yeah, I see. Yeah, I think this just I'm a little confused about the definition then.
Yeah, I feel like the definitions are not very clear in this problem. But does that make more sense?
Yeah, I think like my intuition, at least like when I was doing the problem within time constraint, I can definitely just like immediately came up with the first inequality in the end statement, because like the way I thought about it is that it's like if we have a cycle, that means it's possible that we visit like a vertex V that is reachable from U, like earlier than visiting U. And like, the pre-order number here is kind of like just the visit time in the DFS numbering. And like, and then like for the second inequality, it's just kind of hard for me to build up an intuition. But right now, like if using the new definition, I think the intuition is that it's also just since we are doing this like DFS, it's kind of like we have to visit. Actually, I don't know if anyone can explain.
I think the intuition for like the second inequality is that, or at least for the first inequality, it's that you don't want anything in your subtree to have like some greater visit number, I guess, than you. But then for the second one, it's like you don't want anything in your subtree to have a greater visit than something else in your subtree. I don't know if that makes sense. Like you don't want anything in your subtree to go back above you.
To go back above.
Does that make sense?
So, above V or U?
Above
So,
V, I believe. I don't know if that makes sense or not, but yeah. Go ahead.
Yeah, so it's just it's a little hard for me to think of like it seems like it's just like, I need to make sure in the subtree, meaning like the vertices that can be reached from the root, that can be reached from the root through BFS. I cannot sort of like visit it any later. I cannot visit a node that can be reached from one node in the subtree at any time later than the visit time of all of the nodes in the subtree. It's kind of because I feel like if that's the case, if we don't have any cycle, that means like when we are doing this DFS, we should have reached the like all the nodes possible, meaning that like we will visit all of the nodes. I don't know how to. I don't know how to like build up like a very rigorous wording for that. If anyone has like a better explanation for this, I'm still a little confused, I guess.
I guess one way you could think about it is basically the two conditions is A, you shouldn't be able to get, you can think of like the numberings as like the order you visit vertices.
Yeah.
You shouldn't be able to get to anything later from something you visited before.
I shouldn't get to anything later than something I visited before. Yes.
Or like you shouldn't get to anything in your subtree from anything you visited before. Because
I visited before. Yes.
If you could, then this edge can't be critical because you could just get to your subtree from that other previous. Vertex.
Yeah.
So that's the first inequality, basically.
Yeah.
And then the second thing is that you shouldn't be able to go from your subtree to. You shouldn't be able to go from your subtree to like a previous vertex.
Yeah, to a vertex I visited before the root, I guess. Okay.
Next neighbor and subtree.
Yeah, I think that makes yeah. I think this wording itself makes more sense. I think I just need to. Again, I was confused about the definition. So like with the right definition, I guess I need to reason through the inequality again and like think about how exactly it matches with the wording. But the wording itself makes sense, yes. All right, thanks so much.